So we've gone through all the settings, and I think probably next what we can do is look at some of these files. A couple of different files here under GPS. And because they're Carlson RW5, these can be entered in as under GPS files or under raw file. But when we get started, these are blank. There's nothing here. It just shows raw files, GPS files, level files, and control files. So when we get started on this, we can either right click and say add a raw file and then browse to it. Or I can hit the big red plus and add data, what I want to add. I can say I want to add a raw data file, and I can browse to my files. That's how these were added in. I've got one file that's got traverse work in it and a couple. This is just where I brought in the vectors. So if I double click this, it's really nice. It's going to bring up that data. So here's my RW5 file. And you can see base point 609. And then I shoot point 11, point 12. These are my vectors. I've got the base point to the rover point, delta X, delta Y, delta Z. I've got my it does that. I've got variance and I've got covariance, and all of the vectors. There's my base point 609 to 11 and to 12. And again. So I've got all my vectors there. And they're all from 609. And in my other file, I can double left click that, pulls it right up. And here are my other vectors that it's going to read. I've also got my traverse file. Double click that. This is really nice to work back and forth between the raw files easily when you're in the SurvNet environment. Oh, right off the bat, we start off on points 11 and 12, and we just start at traverse. We've got a lot of angle sets. We've got some side shots. And let's see when we close out. It's been a while since I looked at this. It looks like in this case, when we come back to close out, we're on 15 backsliding 14, and we go back to 11. Now, if you remember, we had that that alias setting where we could use, for example, if instead of 0.11 in the field, we called it 111, that's fine. That's where we would need equals 11 in the description. And if I was to do that, it would read it exactly as if you would have coded it as 0.11 in the field. You get that back to the way it was. So we do that, we come back to 11, we occupy 11, and there's our closing angle back to 12. So that's how we get that closed loop. And if we look at the graphics, you can see that we've got a little bit more redundancy. I think we start there and we work around. There's quite a bit of redundancy in the traverse work itself, which is really nice. So when you start SurvNet, though, you don't see any of that stuff. I mean, it's not like the graphics aren't there. I mean, we have to process it first to see the graphics. So what I can do, let me just erase this, except for my imagery. Okay. All we've got is our cores. And a couple things we can do, we can actually pre-process the raw data first, which gives us all of our pre-processing area if we've exceeded any of our tolerances that we have in our settings. I typically don't do that, honestly, because when we do the adjustment, which is this button right here, it actually gives us the pre-processing as part of that. So at this point, we've started up the project, we've got our coordinate system set, all of our settings are the way we want them. and I think everything is okay, so I can hit the adjust button. And when I do that, it gives me a report. I'm going to close that out for a second. Still nothing is drawn. If I want to draw the graphics, at that point I can hit this pencil, just left click that, and bang, it's going to draw everything in for me. Now, right off the bat, we have the results tab, which is basically just a portion of the report. This is something that I look at first when I first adjust a network, just to get an overall feel of how things are. First thing I'm looking at is the solution. Did it converge? Yes, it converged in 3 iterations. I look at my total observations, my unknowns. Observations minus unknowns, that's our degrees of freedom. We've got a pretty high degree of freedom for such a small network, which is great. I've got my standard error of unit weight for my angles, distances, vertical angles, and my vectors. You see my vectors are a little bit high, and that's just the way this network worked out. This is not a really tight little survey. It's definitely real world. It's not it's not the greatest, but it is okay. I look at my chi-square test right off the bat, and chi-square is also referred to as the goodness test, I guess, for a lack of better terms. But essentially, you can look at your chi-square, and in general, you can say, how did I do? It doesn't mean because you pass, it doesn't mean that everything's perfect. It doesn't mean you don't have a mistake that you can't see because it's an uncontrolled side shot, but it gives you a pretty good idea. And if you fail really, really high, you know you've got a problem. And when we pass, we've got a lower bound of 28 and an upper bound of 65. A passing chi-square test means our middle number is going to be between those. If this middle number is higher than the upper bound, so in this case, if it was higher than 65, it would say failed the chi-square test, optimistic, which means our standard error settings are too optimistic. They're basically too tight, and we're failing, or our measurements are a little bit loose, one or the other. If it says that we failed the chi-square test, if we actually are below 28 in this case, it would also say that we failed the chi-square test, and it would say pessimistic. If you're going to fail, the best way to fail is low. When you see this number in the middle, if something's really wrong in your network, you got a point number that's wrong, you got a busted H, height of rod, that type of thing, you might see this middle value be, 1,000 or something crazy. You can say, okay, not the end of the world, something's wrong, I'll find it, not a big deal. But this is the first thing I look at just to get a general idea how my network did. Once I look at that and I'm passing the chi-square test, I actually go to this clipboard up here and I take a look at the main report. And this is where all the details come in about your network. So right at the beginning, we've got our input data. We've got our, what are we using? We've got these 3 raw files. What is our output? We're outputting a report, which is what we're looking at, by the way. When we hit the adjustment button, if you look right next to the SurvNet.prj, you're going to have a .rpt, which is what we're looking at. You've got that report archived as soon as you hit the adjustment. So you never have to worry about that. We've got a traverse file where we've got a closure, just general information. We've got our, our coordinate system, our units, confidence interval, geoid, all of our project standard errors are right here. This is our pre-processing right here. We've got a couple things that are flagged where we've got a couple of the vertical angles that are above whatever our setting was, which let's take a look at it and see what it was. I can't remember. 30 seconds. So anything over 30 seconds is being flagged. Get that in the main report. That's not horrible. We got some pretty short shots out there. 47 seconds, not great, but okay. So it's telling me nothing's really standing out. I don't have any 2-degree angle conflicts or anything crazy like that. And I'm just going to keep scrolling through the report here and kind of going over the details a little bit so you can better understand them. It's going to give us our control points in 3 different formats. We've got them in lat long, we've got them in geocentric, and we've got them in northern eastern grid. And because of our project settings, we've got those fixed. You can see that here. And as we move on, we are going to be looking at all of our measurements from 11, all of the distance measurements, all of the angles, all the vectors. And one of the things that you'll also see is what we call the standard error. And this is what we call a priori standard error, which means these are calculated values. These values are based on your settings. If you remember, in our settings for our EDM, it was 100th plus 5 parts per million. Well, 100th is going to be, and then we're going to have 5 parts per million, so we're only 249 feet, so it rounds to just 100th in this case. As the line gets longer, here's one that's 588. We've got an a priori standard error value of 200ths. That's what the software is expecting when it does the adjustment. And if we have residuals where we have the adjustment amounts that exceed those a priori standard errors, that's kind of what we want to look at. And we'll get into that a little bit later. So we kind of come up with these benchmark values that we expect for residuals in the adjustment. That's what we're looking at right now. These are computed. They're always going to look good. We get into the mark-to-mark vertical, and these are in seconds. So these are actually what we measured. And these are our a priori standard errors in seconds. That's what the software expects based on our settings. Same with the angles. See those numbers vary. And now we get into the vectors. These are just as measured. So we've got the delta x, delta y, delta z. We've got our variance, delta, XYZ, and our covariance. And this is the bearing and distance of the vector projected to grid. These are all of our measurements. Traverse closures. Because we set up a traverse, we have that information here. Started on, that's actually our back site was 0.11, and we ran through it and we turned our closing angle. So it actually tells us what our closure is. Angular error, 36 seconds, a little bit high, but we know what it is. And our raw unadjusted closure is 1 in 16, 1 in 17,000. So it's not the tightest. And then we get into after angle adjustment. You can see that our closure went up a little bit. That's good. But anyways, we do have that number. If we want to report our raw unadjusted closure, we can say we're 1 in 17,000. We've got that information. We know that we've got a decent loop. As I continue through the report, we are going to see our adjusted geographic coordinates. All the information you need, convergence angle, grid factor, elevation factor, multiply those together, and we've got our combined factor. One thing to make note of is when you are in a geodetic system and you've got state plane coordinates as control, the software isn't intelligent enough because it knows the combined factor at every station. It knows how to scale your EDM measurements. So it's not taking the ground measurement in your raw file and using that and trying to fit that to state plane control with all your GPS. It's actually scaling that intelligently, all automatically behind the scenes, which is really nice. Now we get into our adjusted values here in grid and geocentric, just a lot of information here. Now we're getting into, these are our standard errors. Now we're getting into our 2 sigma values at 95% for all of our points. And you can see there's nothing too horribly high at 95%. Looking at these values, just seeing if something really spikes up really high. You can see some of these get bigger, 27, 28, those are gonna be our side shots. If we look on the map, you know, they're drifting further away from our traverse. Down a little lower here. The next thing we're going to get into is the Alta report. So it's checking every single possible connection. There was a setting there that we only told it to look at the top, the largest 20. So we don't have if you've got 100 points, there's thousands of connection possibilities in that. We don't want to report all of that. We want to look at the worst 20. So it's always going to list these connections from the worst one, and they're just going to get better and better and better. So the worst connection that we have is 14 to 18. And in this case, we have an actual semi-major of 6/100ths of a foot. The allowable, which is the computed value, is 8/100ths. And then it does a simple ratio. If you have a value that's greater than 1, it will show as a failure, and it's going to flag it with an asterisk. So if we did have things that did not meet the 7/100ths plus 50 parts per million Alta criteria, that information is going to be flagged. And so at that point, you have to find out why that might be and manipulate the data. You could maybe take an angle out. Maybe you have to go back in the field, get some more redundancy. There's different ways to attack it. Oftentimes, if you got enough redundancy in your network and something is failing, especially with GPS, you know, quote unquote black box technology, maybe you've got multiple observations to one point and one of them standing out a little bit, go back into the raw data and basically turn it off so that it's not red, run the report again and see if your standard deviations get a little bit better and therefore your connections. Sometimes you can get things to pass that way without going back into the field. But it's telling us everything passed, which is great. This part of the report that we're getting into now is probably the most important. If you remember right off the bat, we talked about the A priori values for our distances, for our angles, for our vectors, everything. The computed values, what it expects. This part of the report, we're showing the residuals. The residual is how much we adjust. So these squares, some of the squares of the residuals is minimized. That's what we're looking for. We want to have the minimum amount of adjustment as possible. And that's what least squares are doing for us. So these are our residuals. These are our mark-to-mark distances. So you can see our residuals are all pretty low. But what does it mean to have a big residual or a small residual? That's where we get into what's called the standard residual. And the standard residual is how we quantify how big it is. So if we get into our vectors, the residual from one of those core stations for 20 miles coming in, it might be, you know, 1/10 of a foot. Well, is that big? Is that small? Well, that's how we quantify it with the standard residual. So in this case, let's find one like, let's say, 11 to 12. That's telling us this value right here is 2/10 of what was expected. If we go all the way to the top of the report and we look at these values, it's expecting 1/100th of a foot. And we end up with 0.002, we're 2/10 of what's expected. So when I look at these reports, one of the things I key in on is not just the residuals, but the standard residuals. I want to make sure the standard residuals, I don't want to see them skyrocket. When I'm at 1, that means the residual value is the same as the A priori. And that means you're basically right at where you would expect to be. So if we look at these standard residuals, they're all beneath 1, which is fine. We got one that's approaching 1. Horizontal angles, it's the same thing. Okay, so here is a value of 14 seconds. Here's 16. These are my residuals. You know, okay, that's great. Well, what's the standard residual? That's what I care about. That one's a little bit over 1. So we're all looking really good. Anything, if you have a standard residual that's 2 or greater, it's going to flag it. And if you've got something really wrong in your network, you'll see these skyrocket. You'll see a bunch of 2s and 3s, that type of thing. that means you got something going on. Same thing with the vertical angles. We've got our residuals, and we've got our standard residuals. All the standard residuals look great. Vectors are the same thing. I did inflate the vector standard error a little bit in our settings, because the vectors are where we've got a little bit of where the weakness is really in this network. We only had one vector into each of those points, so we didn't spend a lot of time on them. Wouldn't have been a bad idea to get some redundancy bringing those points in. But these are our residuals. These are in meters, and you can see. So these are there's a centimeter. You can see our standard residuals are a little bit higher than anything else. There's one that's flagged. See how that's over too. But there's nothing in this report that really stands out as being bad at all. It's not the tightest. It's pretty much a real world situation. This, at the very end of the report, is where we're getting into kind of what we see in this general results tab as soon as we hit the adjustment button. You'll notice our standard error of unit weight, as we can maybe expect, is a little bit higher when it comes to the vectors, and we saw that in the standard residuals. And lastly, we're reporting our side shots. So you can have a completely blown side shot, just like in any other network. It could be off by 100 feet. SurvNet has no way of knowing it. It's going to say everything's fine. We don't have any control over a side shot. So we've got a pretty good looking report, and I don't see any problems with it. At this point, if I wanted to, and I'm not sure what I have in my points here. Let me see if I've got points. I do. But if that coordinate file was blank, and if I wanted to bring in the points into my drawing, there's a couple different ways. Right now, these are not in they would not be in the coordinate file normally. That coordinate file was populated because I populated it in the past. But this is a brand new drawing. The coordinate file wouldn't have these points in it. These are just graphic at this point. But if I want to bring those in, there's a couple of different ways I can do it. I can go back into my settings, go to output options, and tell it to write. Select my coordinate file. I'm not going to do it, but if I had that, and then if I run the adjustment again, it's going to write to the file. The other way I can do it is I can go right up to my points menu, and I can go to import text ASCII, and I can browse. And I am going to browse. I've got my project folder set up so it goes right to the SurvNet folder, the SurvNet.nez file. And it gives me a preview. I can say open, then it's going to bring in all my points. Those are state plane coordinates. But let's play around with this a little bit. If we get into the results, you see we are passing the chi-square. Let's just change some settings, and you can see how things change. We go into our standard errors. Let's set this to 0. That means we're not scaling our GPS at all. We're not going to say that it's, we're going to let that variance covariance speak for itself. It's usually overly optimistic. I'm going to say okay. If I run this adjustment again, my lower and upper bounds are the same. My middle value is above my upper bound. I am failing the chi-square test. Same exact information. Same exact information. Look at my vector standard error of unit weight. I think it was 1.6 before, now it's 2.5. So it had to put more adjustment into the vectors because I basically altered the settings. So let's get into the report again. And let's look at our vectors. Look at all these things that are flagged now. Same data, but now we've got things that are flagged. Our residuals will change some, but basically we're holding them to a higher standard and we're not meeting that standard. just because we changed the setting. We just want to make sure that these settings are reasonable. I honestly think 2 is a little bit high, which is what I had it before. If I set it to 1, that's really more realistic. I can run the adjustment again. We are passing the chi-square test still, a little bit higher in the middle. And if we go take a look at our vectors, now we have a few of them that are flagged. Yeah, they're all right around 2. There's one that really stands out. Now we shot 61 to 11 multiple times. We could actually get into the raw data and turn that off if we wanted to. 61 to 11. Try to get rid of it. Which one was 61? That was the Wisconsin. There it is. Let's do this. I can highlight a line. If I say add data off, it's going to put a toggle in there. It's not going to read any of that data now. I'll save that file. If I run it again, we're going to get slightly different numbers. You can see the chi-square got a little bit better because I got rid of a shot that might be a little bit weak. And we don't have that value that was in the forest because I took it out of the equation. So that's just an example how you build in that redundancy, build in a ton of it. When you get it in the SurvNet, you start having trouble. You can see where you've got some outliers. You might want to turn some data on and off, tighten things up. That's a really, really handy way of doing things. Really, really good, powerful tool. So, and you can see how fast it is. I mean, once you get it set up, you can change your settings. You can turn data on and off in the raw data, manipulate it, get it the way you want it. If you've got a blunder, you might have to go back out in the field and get it corrected. Honestly, 9 times out of 10, the problems that people have when they don't converge and they've got a big mistake is point numbering. And I mean, if you think about it, everything we do is, we're not writing down things in the field book, and very few people do anymore, although some people still do. We're not transposing numbers anymore. We're not writing things down. We're not having trouble. Is that a 3 or is that an 8? Everybody's pretty much digital. So realistically, when we have trouble, it is somebody called at point 10 when it was really point 11, and that blows things up. Rod heights, instrument heights, antenna heights, those can also cause issues as well. Those are typically the problems. If it's a point numbering error, we can fix that, and we can make an adjustment that looks like it's absolutely junk turn into gold with just a few clicks.